Good day, everyone. This is Professor Friday coming at you one more time. Today we're going to be solving oh boy, let's use all the right terms that we can. Well, it's a differential equation. It is second order. I see that the coefficients are not constant, but I do see that the power of x matches the order of the derivative. That would make this a second order, non-homogeneous Cauchy Euler equation. So with that in mind, x squared y double prime minus 5xy prime plus 8y is equal to x squared plus x to the sixth power. So first thing we do anytime we have a non-homogeneous equation is we go straight to the associated homogeneous equation, which would be replacing the right-hand side with 0. Excuse me. So replacing the right-hand side with 0. For Cauchy Euler, there are a couple different ways that we can do it. The first way that we could do it is for a Cauchy Euler equation, we operate under the assumption that y is going to be x raised to the r power. That way we can do y prime is equal to r times x raised to the r minus 1, and y double prime can be r times r minus 1 times x raised to the r minus 2 power. The reason that we make the assumption is because every time you differentiate a power, the power goes down by 1. But every derivative has a corresponding multiple of x on it, which is going to bump that power right back up. So operating under this assumption, let's copy down the expression that we would get. So the first term, x squared times r minus 1 times x to the r minus 2 minus 5x times r times x to the r minus 1 plus 8 times x to the r. That's all going to be equal to 0. So let me reiterate the thing that I just said. Every time we differentiate a power, power goes down by 1, but every coefficient is going to bump it back up to the appropriate power. So all three of these terms are going to have a greatest common factor of x raised to the r power after you combine them into one single x term, or x factor, I guess. Ha! X factor with Joe Rogan and Professor Friday. So, with that x factor being done, we factor it out, we're left with this. We'll distribute the r through this set of parentheses and combine some like terms and hopefully get a nice looking equation that we can solve for r. Oh, yeah, that's hot. Yeah, we can solve this for r no problem. We get a factor of r minus 2 and a factor of r minus 4, telling us that r is equal to either 2 or 4. So with that in mind, that tells us that our complementary solution is going to be some linear combination of x squared and x to the fourth power. Boom. Now, given that this is a Cauchy Euler equation, it is not possible to express the left-hand side in terms of annihilators unless we make kind of a nasty substitution. And by kind of a nasty one, I mean you should practice it a few times because it becomes considerably less nasty. Instead, I think what I'd like to do is use the variation of parameters one more time because it is just such a good thing to practice. The VOP assumption is that we are going to take a nonlinear combination of our complementary solution, and we are going to attempt to turn that into the particular solution. However, as I am out of space on this page, I am going to write down that VOP assumption one more time at the top of this one. Top for the VOP. Particular solution takes the form u1 x squared plus u2 x to the fourth. That's where u and u are both functions of x. So we differentiate first times derivative of the second plus second times derivative of the first, and first times derivative of the second, and second times the derivative of the first. Now, I've mentioned this in other videos, but one of the big things that we need to try to do is avoid a u1 double prime and a u2 double prime. So what we're going to do is grab everything that has a u prime in it x squared u1 prime plus x to the fourth u2 prime. We're going to set that equal to whatever we want. My favorite thing to set things equal to when I can set it equal to whatever I want, we'll set it equal to 0. I think that'll work out pretty nicely. Then we wind up with the fact that the particular solution, prime, is going to be 2x times u1 plus 4x cubed u2. We differentiate this again, and then we'll plug it back into the original differential equation. So this will be differentiating the 2x, we'll get a 2. Differentiating the u, we'll get a u1 prime. Same thing over here. Differentiating the 4x cubed will get us this. And differentiating the u2 prime, we'll get u2 prime. So we're going to take this second derivative, this first derivative, and this 0th derivative and plug it all back into the original differential equation. So first thing I'm going to do is recopy the original differential equation. X squared times y double prime minus 5x times y prime plus 8y is equal to x squared plus x to the sixth. All right, I hope you brought your long paper because the left-hand side is going to be awfully long here. X squared times this double prime, 2u1 plus 2x u1 prime plus 12x squared u2 plus 4x cubed u2 prime minus 5x times the first derivative, which, after our little substitution, became this, plus 8 times the original function. Original function was u1 x squared plus u2 x to the fourth. All of this is supposed to be equal to x squared plus x to the sixth. Good stuff. All right, now, if everything works the way that it should, then we should see all of the terms cancel out on the left-hand side except for the u1 prime term and the u2 prime term. So because I am ridiculously confident, I'm going to go ahead and do this. u1 prime, the only term that I see is this 2x. But that 2x also has an x squared out here, so we'll call that 2x cubed. For the u2 prime term, there's only one of those. It's 4x cubed. 4x cubed has a buddy out here, so we'll actually call that 4x to the fifth power. Now, let's group all of the u1 terms together. I see a 2 with a coefficient of x squared, so 2x squared. Down here I see 2x with a minus 5x for a coefficient. That'll be 10x squared. And then over here, 8 times x squared. Can I get a woot woot? And do the same thing for u2. u2, I see a 12x squared up here with a coefficient of x squared. We'll call that 12x to the fourth power. Down here I see a 4x cubed with a coefficient of minus 5x. So we'll go ahead and call that minus 20x to the fourth. And finally down here, x to the fourth, coefficient of 8. I'm just so excited. That's all still equal to x squared plus x to the sixth power. So the great news is everything worked out the way that I had hoped it would. These are going to cancel out completely, and these are going to cancel out completely, and we are left with just u1 prime times 2x cubed plus u2 prime times 4x to the fifth power is equal to x squared plus x to the sixth. Combining that with the assumption that we made earlier, or rather the substitution that we made earlier with this guy right here, we can now set up a system of two equations with two variables, those variables being u1 prime and u2 prime. I'm a little low on room on this page, but I think I can still make it happen. So this will be x squared times u1 prime plus x to the fourth times u2 prime is equal to 0. And then this equation, I'm going to do something a little bit weird to this equation. I'm I'm actually going to multiply by 1 over x squared to begin with. I'll explain the reasoning in just a sec. That's x squared up here. 2x u1 prime plus 4x cubed u2 prime is equal to 1 plus x to the fourth. So the justification that I'm going to give that is that when written in this form, the left-hand side winds up being the Wronskian of our complementary solution one more time. Now, the reason that we had that extra x squared show up here is simply the nature of the Cauchy Euler equation. The things that wind up not canceling out are always going to be part of the first term of your Cauchy Euler. So in this case, we wound up with an extra factor of x squared that prevented us from seeing the actual Wronskian of those two. So by dividing by the x squared at this step, it was able to turn this into exactly the Wronskian. Now I'm going to take that system of equations and turn it into a matrix, because that's just what linear algebraists do all the time. So it was x squared, x to the fourth, 0, and then we had 2x and 4x cubed, and then we had 1 plus x to the fourth. So if you wanted to shortcut this in the future, coefficient matrix is the Wronskian. Up here we'll have 0, and down here we'll have whatever the highest power of x was, in this case x squared, times whatever the non-homogeneous part was. Now this is specifically for a second order equation. If this had been third order, we would see an x to the minus 3 up here. So first thing I'm going to do is let's divide the first row by x squared. Let's divide the second row by x. There we go. Then we'll take negative 2 times the first row, add to the second row. So overall first row is not changing. Negative 2 times that, add to that. Negative 2 times that, add to that. Good, good. Next, I'm going to save us a step by saying let's take negative a half of the second row and add to the first row. That'll get us a 0 before it gets us that leading 1. So 1, 0 will be negative 1/2 x to the minus 1 minus 1/2 x to the third. Oh yeah, this is looking real good. And for funsies, why don't we just go ahead and do the other operation that we need, which is take row 2 and divide it by 2x squared. Yeah. So this will give us half of x to the minus 3 power and half of, oh, just x. That's good. Interpreting both of these rows, this lets me know that u1 prime is equal to negative 1/2 x to the minus 1 minus 1/2 x cubed. Second row tells me that u2 prime is equal to half of x to the minus 3 power plus half of x. Integrating each of these will let me know what u1 is equal to. So integrating term by term, we'll get negative 1/2 natural log of the absolute value of x. I find the absolute value to be both superfluous and redundant. That's my pretentious voice. We'll do the same thing for u2. We'll integrate each of these terms. We'll get negative 1/4 x to the negative 2 power, and then we'll see a plus 1/4 x squared. Now, keeping in mind that these two things came from the original assumption of the variation of parameters, which I'm going to show you right back here. The original VOP assumption was this guy right here. So I'm going to take each of those functions that I just found, multiply by the appropriate power of x, and we'll see what we get. Our particular solution is going to be u1 times x squared. plus u2 times x to the fourth. Let's distribute, see if we have any like terms that could potentially be combined. So that'll be negative 1/2 x squared, natural log of x, minus 1/8 x to the sixth power. Let's see, minus 1/4 x squared plus 1/4 x to the sixth power. Good. All right, some additional explanation is probably needed here. These two guys are like terms and can be combined. Plus 1/8 x to the sixth power. At this point, I am going to stop writing this term. That seems really biased on my part. Do I have a bias against this term? The answer is no. The reminder is that the complementary solution involves a generic constant times x squared plus a generic constant times x to the fourth power. Now if I take a generic constant times x squared and I subtract 1/4 x squared, what happens is this term can get absorbed into this term by saying they are like terms, and a generic constant minus 1/4 is still a generic constant. So as a result, when I write down the complementary solution, we won't see that term show up anymore. Or rather, when I write down the general solution, we won't see that term show up anymore. It's not incorrect to write it there, but I know a lot of textbook authors tend not to write that because it does get absorbed back into the original term. So here we have our general solution for this differential equation. Now, I would like to point out a couple of things that hopefully will make sense in the context of the problem. Your particular solution involved in x to the sixth power. Well, the original function involved in x to the sixth power. We also had an x squared up here, but because x squared was part of the complementary solution, there we go, complementary solution, generally speaking, when this shows up again, we wind up with something times a natural log of x, which is why hopefully it makes a lot of sense that an x squared natural log of x term showed up as part of the particular solution. So I hope this was educational. I hope you all enjoyed, and I'll see you all soon.